So in this lecture, we're talking about arrays and linked lists. In this video, we're going to talk about arrays. So here's some examples of declarations of arrays in a couple of different languages. Along with, we can see the one-dimensional array laid out with 5 elements in it, and then a two-dimensional array with 2 rows and 5 columns. So what's the definition of an array? Well, we've got basically a contiguous array of memory. That is one chunk of memory. That can either be on the stack or it can be in the heap. It doesn't really matter where it is. It is broken down into equal-sized elements. And each of those elements are indexed by contiguous integers. All 3 of these things are important for defining an array. Here, in this particular example, we have an array whose indices are from 1 to 7. In many languages, the same indices for this particular array would be from 0 to 6. So that would be 0-based indexing. But 1-based indexing is also possible in some languages, and other languages allow you to actually specify what the initial index is. What's so special about arrays? Well, the key point about an array is we have random access. That is, we have constant time access to any particular element in an array. Constant time access to read, constant time access to write. How does that actually work? Well, basically what that means is we can just do arithmetic to figure out the address of a particular array element. So the first thing we need to do is start with the address of the array. So we take the address of the array, and then we multiply that by, first, the element size. So this is where the key part that every element was the same size matters. So that allows us to just do a simple multiplication. Rather than if each of the array elements were of different sizes, we'd have to sum them together. And if we had to sum together in items, that would be order n time. So we take our array address, we add to it the element size times I, which is the index that's of interest, minus the first index. Okay? If we're doing 0-based indexing, that first index isn't really necessary. I like this example because it really shows the more general case where we do have a first index. So let's say, for instance, we're looking at the address for index 4. We would take 4 minus the first index, which is 1, which would give us 3, multiply that by whatever our element size is, and then add that to our array address. Now, of course, we don't have to do this work. The compiler or interpreter does this work for us. But we can see how it is that it works in constant time. Many languages also support multidimensional arrays. If not, you can actually kind of roll your own through an example I'll show you here where you do your own arithmetic. So here let's say that the top left element is at index 1, 1. And here's the index 3, 4. So this means we're in row 3, column 4. How do we find the address of that element? Well, first off, what we need to do is skip the rows the full rows that we're not using. So that is, we need to skip 2 rows, or skip 3, which is the row index, minus 1, which is the initial row index. So that gives us 2 times 6, or 12 elements we're skipping for those rows, okay, in order to get to row 3. Then we've got to skip the elements before 3, 4 in the same row. So there are 3 of them. How do we get that? We take the column index, which is 4, and subtract it from the initial column index, which is 1. So this basically gives us 15. 6 for the first row, 6 for the second row, and then 3 for the third row before this particular element. We take that 15 and multiply it by our element size, and then add it to our array address. And that will give us the address of our element 3, 4. Now we make kind of a supposition here, and that was that the way this was laid out is we laid out all the elements of the first row, followed by all the elements of the second row, and so on. That's called row major ordering, or row major indexing. And what we do here is basically we lay out 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, and then right after that in memory, 2, 1, 2, 3, 2, 4, 2, 5, 2, 6. So the column index is changing most rapidly as we're looking at successive elements, and that's an indication that it's row major indexing. We could lay out arrays differently, and some languages or compilers actually do that, where they would lay out each column in order. So you'd have the first column, then the second column, then the third column. And so that then, the successive elements would be 1, 1, 2, 1, 3, 1, followed by 1, 2, 2, 2, 3, 2, and so on. So there we see that the row index is changing most rapidly. And this is called column major ordering. How long does it take to perform operations? We already said to read any element is order 1, and to write any element is order 1. That is a standard feature of arrays. What happens if we want to add an element at the end of an array? So let's say we have allocated 7 elements for an array. We're only using 4 of them. Okay, so we have kept track that we're using 4, and we want to add a 5th element. And again, there's room for 7. Then all we need to do is just add it. So, and then update the number of elements that are in use. That's an order 1 operation. If we want to remove the last element as well, that's an order 1 operation because we just update the number of elements that are in use. And so that's an order 1 operation. Where it gets to be expensive is if we want to, for instance, remove the first element. So we remove the 5 here, and what we've got to do then, we don't want to have holes left in it, so we need to move the 8 down, move the 3 down, move the 12 down. That's an order n operation. Same thing would happen if we wanted to insert at the beginning. So we would need to move the 12, move the 3, and move the 8 to make space for our new element. So that also would be order n. And if we want to add or remove somewhere in the middle, again, that's order n operation. If we want to add exactly in the middle, we have to move in over 2 items, which is order n. Same thing for removal. So arrays are great if you want to add or remove at the end, but it's expensive if you want to add or remove in the middle or at the beginning. However, remember our huge advantage for arrays is that we have this constant time access to elements to either read or write them. In summary then, array consists of a contiguous area of memory, because if it were non-contiguous, then we couldn't just do this simple arithmetic to figure out where we're going. We have to have equal size elements, again, so our arithmetic works, and indexed by contiguous integers, again, so our arithmetic works. We have constant time access to the element, constant time to add or remove at the end, and linear time to add and remove at any arbitrary location. In our next video, we're going to talk about linked lists.